Okay, good morning, everyone. Let me start where we left on Tuesday. We were going through some review of some of the linear algebra, specifically matrix manipulation and matrix properties. And the last thing I covered was finding inverse of a 2 by 2 matrix, which I said will happen here. So you will need to find inverse of matrices that are 2 by 2. I know some of you or some calculators can find inverse of matrices, but a quick way of finding the inverse of a 2 by 2 matrix, as you can see from the last item. So this was the matrix AB, the first row, CD, the second row. And what we found as the inverse, if you look closely, you can see that the diagonal terms have switched places. So A went where D used to be, and D came to where A used to be. And the off diagonal terms stayed in place, but what happened to them? Their sign switched. So the diagonal terms switch places, the off diagonal elements switch sign, and divided. The whole thing is divided by the determinant of matrix A. Now, how can you tell if we did this correctly? You need to take this matrix A inverse and multiply it by A, and if the result is the identity matrix, this is the correct inverse. If it is anything else, this is incorrect. So as a warm-up exercise and help you wake up a little bit more, why don't you go ahead and multiply A inverse by A? I'll give you 30 seconds, and this way we'll see if we did it correctly or not. And you already know how to multiply. You already knew, but we also reviewed how to multiply matrices. So what would be the dimension of the resulting matrix? A inverse times A. How many rows, how many columns? If you remember, we said an A matrix, look here, an A matrix that is M by N, number of rows that is M and number of columns that is N, can be multiplied by a matrix B where number of rows is N. So number of columns of the first matrix, number of rows of the second should match, and the dimension of the resulting matrix is defined by number of rows of the first matrix and number of columns of the second matrix. So M by P. So having said that, what would be the dimension of the resulting matrix here? It has to be 2 by 2. So let's go ahead and find, so we know it's a 2 by 2 matrix. So what is row 1, column 1 of this resulting matrix? And how do we find it? So for row 1, column 1, we go to row 1 of the first matrix, column 1 of the second matrix, and multiply them at one element at a time, which means this would be D gets multiplied by what? So D times what? D will be multiplied by A minus B times what? C. So row 1 of the first matrix gets multiplied by column 1 of the first matrix. So it gets multiplied by C, which is this element. Now let's go to row 1, column 2. Again, row stays the same from the first matrix, but it gets now multiplied by column 2. So it becomes D times B minus B times what? This is very critical. You need to be very clear on that. So if something doesn't make sense, let me know. But I need your answer. So what is the second element here? Minus B times what? Minus B times D. So minus B times D. And that's row 1, column 2. So let's go to row 2, which means this row will be involved. And the first and for column 1, it gets multiplied by column 1. So it's minus C times A minus C times A minus A times C and minus C times B plus A times D. So does this look like the identity matrix to you? Probably not on the surface, but if what we haven't included yet is the determinant of matrix A. So let's go ahead and find what the determinant would be. So let's go ahead here and find determinant of matrix A. What is this determinant? It's A times D minus B times C. Look at the diagonal terms A and D, and the off diagonals are C and B. So multiply the first two, subtract from it the second. So what we need to do is to divide this matrix by A times D minus B times C. So look at row 1, column 1. We have A times D minus B times C divided by A times D minus B times C. So this becomes equal to 1. DB minus BD is equal to 0. AC minus CA is equal to 0. Of course not. Let me see if we made a mistake here. So because minus CA minus AC is not 0. So let's go to row 2, column 1. So row 2, column 1 is this row multiplied by column 1 at A. So the first element is minus AC, but the second element is plus AC. So I made a mistake here. I apologize. So let's correct that. So plus AC. So that's 0 now. And the last element is minus CB plus AD. That gives us negative 1. So what did we do wrong?
So the minuses cancel. And it's positive.
So which
Like 80 cancels 80, right? And there's minus BC and minus CB.
here?
Yeah.
You're checking.
And then you divide it by minus BC. So it would be 1.
Oh yeah, the order is different. So it's exactly the same thing. It's just the order is different, right? So it's minus BC, AD, AD. So it's just the order. So I need my cup of coffee too, yeah. So this is 1. So this is the identity matrix, which tells us we did find the inverse of matrix A correctly. So that was a practice of finding an inverse. Okay, so that was part of what we did last time. But what was more important is this method of modeling. We said we want as the last and third method of modeling to look at a method called state space modeling. And the basic idea is to use or represent the model of the system in the form of a collection of first order differential equations. And that's why the first part of a state space model is a two-part model. The first part of the state space model, the highest derivative in it is 1. So x dot, which is x, where x is state vector, x dot is equal to ax plus bu, where again x is the state vector and u is the input. So in order to have the first part of the state space model, we need to have a and b, which are in general matrices. And we haven't talked about that, but the dimension of those matrices matches the order of the system. And I'll bring that up again. Now, the second portion of the state space model basically identifies the output as a function of a state vector. And remember, we said that repeatedly, that the output is one or more than one, a selection of state variables. We said that repeatedly. So that basically tells that story. Which one or ones of state variables will generate our output? What is output as a selection of state variables? And this was the very first practice. We said if this is the model of the system, the first equation on top left, ax dot plus bx equal u, where x is the state variable because it's just one, we can't call it vector. So it's a state variable here. How can we rewrite this equation to resemble the first part of the state space model? The only thing we had to do was to divide this by a, so x dot is just by itself and on one side and push everything on the other side. So a, capital A in our case simply is lowercase b divided by a with a negative sign, and capital B is 1 over a. So it's algebra basically. So you have your equation, you rewrite it through algebra and find the first portion of the state space model. And there is only one choice here. Our output can't be anything other than x, which is the only state variable we have. So we simply write y is equal to x, and there is nothing after that. So it's plus 0 times u. So y is equal to x plus 0 times u. So c is 1 and d is 0. So we found now the last two that we needed to know to have a complete state space model. So again, let me repeat by saying that having a state space model means having A, B, C, and D, the capital. A, B, C, and D. Once you have them, you have your state space model. The next example problem that we solved was this, based on this second order differential equation. We know by now very quickly that this is a model of a mass damper spring system where a force is the input, a force is applied. So to distinguish our motion variables from state variables, I call displacement p and velocity p dot to separate them and keep away the potential ambiguity. So with that in mind, the differential equation became mp double dot plus bp dot plus kp plus is equal to force. And we introduced our state vector and identified our input, and we said, for now, let's assume the output is simply displacement. And that allowed us to find x dot, which was p and p double dot. So we said, okay, p dot is our first dot variable. We called it x1 dot. And p double dot is our second, so we called it x2 dot. So we found x1 dot is equal to x2. It's fairly easy to see that x1 dot, p dot, is equal to the second member of x. So we said, okay, we know x1 dot is equal to x2, where this is x2. And we know x2 dot can be found by going to the differential equation at the top. So x2 dot, which is p double dot, is equal to 1 over m f minus bp dot minus kp. And remember, our objective is to write these two in terms of x. So we said, okay, what is p dot? P dot is the second member of x, so it's x2. What is p? It is the first member of x, so we called it x1. And that allowed us to assemble this matrix. Basically, this matrix, which is our matrix A, tells this story. It tells us that x1 dot is equal to x2. So x1 dot, which is the first member of x dot, is equal to second member of x. So by simply having this first row as 0, 1, which then gets multiplied by x, you simply say x2 dot is equal to, x1 dot is equal to x2, and there is no u involved, so the first row of matrix B is also 0. So simply by looking at this line, this equation that x1 dot is equal to x2, you found the first row of both matrix A and matrix B. Now the second row of matrix A and second row of matrix B came from this, rewriting the differential equation. So 1 over m got multiplied by u, minus b over m got multiplied by x2, therefore it's here because it's x1, x2 here, and minus k over m got multiplied by x1. So we got now the second row. Now, because we had decided that y is going to be p, which is the first member of x, we immediately found matrix C also. Matrix C is a row matrix, generally speaking, gets multiplied by the column matrix x, and that basically gives us this line. And there is no u involved. I told you last time, let me repeat that for almost all cases, d is going to stay equal to 0. So there would be no d. D always is 0, either as a scalar or as a matrix if we have more than one input. So we asked this question, what if x2 was our output, if velocity was output? And I showed you that the only thing would change, nothing will change in A and B, because remember, the first portion of the state space variable simply tells what the system dynamics is, how the system changes over time. The only thing that changes to tell the story that now we want velocity as output is this. Only matrix C will change, and to make that happen, you just switch place 0 and 1, and you basically say y is equal to x. So that's the review of what we did to introduce the concept of state space. Any questions? Anything that is not clear or you need further explanation? Yes, sir.
How did you get x equal to the matrix B over P dot, I guess?
Can you point me to the line? To the right here?
Up one.
Here?
Yeah.
How did we decide that our state vector was made of position and velocity?
Yeah.
Okay, that's a very good question. So the question, if I want to repeat it, is how do we know that the state vector, which is a collection of our state variables, is going to be p and p dot and nothing else? Now, the first thing we know is because this is a second order system, how many state variables do we have? We have 2. So that's the first thing we know. Now we need to know which variables are our state variables. And I told you where you can look is this, the differential equation. So you can look to see what variable or variables are being differentiated in the form of differential equation. So you can see that the highest derivative is p double dot. So that immediately tells you p dot is being differentiated. So p dot immediately becomes one of the state variables. But if you look closely, you can see also p is being differentiated in order to get to p dot. So that's another reason. That's how we know that also p is another state variable. Now, one thing I want to bring to your attention is that this order doesn't matter. You can put p dot on the top and p at the bottom. What will then switch is the row and columns of these matrices. But there is no set order that the one variable should be first or another variable should be next. Okay, so let's move forward. So we did talk about finding inverse of matrices. Now we want to have another practice problem with finding or deriving the state space model. Now, this is our system. We have already solved this problem in the sense that we have already found the differential equations for this system. So how many differential equations are involved? Two differential equations, and they are both of what order? Second order. And do you remember when we found the transfer function for this system? I think this is a good place, this example is a good example to contrast these three methods of modeling. When we worked with differential equations, our end result was two second order differential equations that were sitting by each other, but were not part of a unified equation. Can you look back and see? Should I do that? So which slide was that? I think it was slide 41, the first time that we looked at this. Yes, look at it. This is in my annotated slides. This is number 41. So the end result, the model is a collection of two equations. So the first equation basically says how Q1 double dot is a function of Q1 and Q2. Look at that. That's the story that equation tells. The second equation basically tells you how Q2 double dot is a function of Q2 dot, Q2, Q1, and U. So in order for the entire system, entire model to work, you have to have these two second order differential equations and work with them if you want to find response, for example. If you want even a subset of behavior, if you wanted, for example, to know as mass 1 moves, how mass 2 will follow or not follow, you have to still solve both differential equations because they're coupled differential equations. Can you see that? So it's not a very friendly model to work with, even though it has all the information you want, but it takes a bit of work. Now, the second thing we did, the second method of modeling involved what? What was the second approach of modeling? It was called a transfer function model. And the benefit of the transfer function model was you can get to the exact model, the exact behavior that you wanted. So we were able to find three different transfer functions. So look at equation 3 on this slide. That equation essentially tells you, is the story of relationship between Q2 as input and Q1 as output. It basically tells you, as you move the second mass, how the first mass will follow or not follow. That transfer function is that story. Okay, and we could also find another model or other models that we needed. So in this next slide, we found G1, which is the relationship between road roughness and the change in displacement of mass 2. So that's G1S. So the benefit that the transfer function brought was to give you focus and ease of seeing relationships. So it's easy to see that the relationship between U and Q2 is a fourth order system, while the relationship between Q2 and Q1 was a second order system. Let me bring that back up again. So the relationship between Q2 and Q1 is a second order system, while the relationship between U and Q2 is a fourth order system, and so is the relationship between U and Q1. It is also a fourth order system. And the order of the system does matter. The type of behavior that you can expect from one system versus the other, it heavily depends on the order of the system. And the speed, the type of response, the kind of vibration you see, it depends. So we contrasted so far the differential equation and the state space model. I'm sorry, the transfer function model. I keep mixing these up. Now, when it comes to state space, you bring another level of clarity to the equation. You can basically, in a way, simplify the behavior by bringing it down to a first order system, even though the order of the system doesn't change. The order of this system, depending on where you look, still is a fourth order system, but you bring similarity to first order system so you can deploy the tools that you know of the first order system. So that's the benefit of using a state space model. Okay, so why don't you please copy the model that you have at the bottom of this slide or elsewhere on your notes. And our goal is to find the state space model for this system. So I'll give you a minute to bring the equations, and I'll do the same here. And then we'll work on finding the state space model. Is this equation correct? The two equations. If you have the model from what we found in the past, is this what we found in the past? Any missing terms or signs? Okay, so we have the two second order differential equations. Double check one more time. So K2, 3, Q2, Q2, Q3, Q2, and K2. Yep, we got it. So what is our goal? What do we want to create? State space model, which looks like what? It will look like this. So the state space model in general for any system looks like this. So x dot is equal to ax plus bu, and y is equal to cx plus du. That's the form of the model we want to have. Okay, so we need to make some groundwork first. So the first question is, what is our input? Input? Everybody? Yeah, u of t is our input. So it so happened that our input is already called u, so it's not an ideal choice, but our input is u, which is the roughness of the road in that example. Okay, input. Now the next thing is, what are the state variables? State variables of Which one? Absolutely. So it's going to be Q1. We can go Q2 that next, or Q1 dot next, then Q2, then Q2 dot. And the state vector is going to be always a column vector. So to just make it easier to write, I wrote it as a row vector with a little t to say that it's really a column vector. It's not a row vector. So far we talked about the input, the state vector, and now it's time to discuss and decide about the output. So what could be the output of this system? So that tells us what y is. So how do we know? How do we choose the output? Of course, it depends on the purpose of the modeling, but there is a limited number of selections that we could have. So y could be any of these guys, any of these members of state vector, either one of them or more than one of them. So it could be one of the four, two of the four, three of the four, or all of them. So let's, for now, keep it a question mark. Once we have the model, we'll decide, and I'll show you how matrix C could change depending on what you choose as your output. Okay, let's move forward. So we need to first of all write what x dot is. So x dot is equal to what? So if x1 is q1, so let's write this as x1, x2, x3, and x4. If x1 is q1, what is x1 dot? Exactly. What is x2 dot? X3, Q2 dot, and X4, Q2 double dot. That is the meaning of X dot. So now we are going to have a 4 by 4 matrix here. Maybe it's too early to draw the second part, so we'll just put the opening bracket. So we need to have a 4 by 4 matrix. Why? Because A needs to get multiplied by X, where X is 4 by 1, so it has 4 rows, 1 column. So in order for this 4 by 1 to come from a 4 by 1 X, we need to have a 4 by 4 matrix A. So the dimension of matrix A is the order of the system, and it's a square matrix always. So A always is going to be a square matrix of the same dimension as the order of the system. So A is going to be a 4 by 4 matrix. Okay. Based on what we did with the mass spring damper system, can you tell me what should go as the first row of this matrix?
0, 1, 0, 0.
It would be 0, 1, 0, 0. Why? Because remember, A gets multiplied by X. And what is X? X is going to be, I'm going to, just for this time, write what X is. This is going to be Q1, Q1 dot, Q2, Q2 dot. That's X. See, we are basically saying Q1 dot is equal to Q1 dot. Because 0 gets multiplied by Q1, 1 by Q1 dot, 0 by Q2, and 0 by Q2 dot, and the result gets added to each other. So you can see that Q1 dot is simply equal to Q1 dot. That's the story that the first row tells. In other words, the first member of X dot is the same as the second member of X. That's an obvious relationship. Okay, how about the first element of U? Because remember, we need a column vector here that gets multiplied by U. So what should go as first row here? So in the relationship that Q1 dot is equal to Q1 dot, what do I need to add to keep that relationship? That thing will be multiplied by U, by the way. In other words, let me write the equation here, and I'll erase it in a second. But this is the question. The first part tells this story, that Q1 dot is equal to 1 times Q1 dot plus question mark times U. What is that question mark? Just look at it as a math problem. Q1 dot is equal to Q1 dot plus what? Absolutely. There is no other choice. So therefore, this guy has to be equal to 0. So let me erase that so we don't have to deal with the clutter on this slide. Okay. While we're at it, let's look at the third row of this matrix. Now, what is Q2 dot equal to? It is equal to the fourth element of X. So what should I write here to reflect that? I need 4 elements. Did you say 0, 0, 0, 1? And what should go here? The same question that I asked about Q1 dot. So that should be also 0. So we completed half of matrix A and B just by writing the obvious relationship between the first and third element of X dot and elements or members of X. Now we should start with the row 2 and row 4. So what is row 2? Row 2 basically tries to find Q1 double dot in terms of Q1, Q1 dot, Q2, and Q2 dot, and U. So where do I go to find that information? How can I find Q2, Q1 double dot as a function of all of these variables?
The model.
Absolutely, the first differential equation. So what do I need to do? I need to rewrite the differential equation, so I simply have Q1 double dot singled out. So Q1 double dot is equal to 1 over m, and I'll take the terms from the left to the right. So 1 multiplied by m times minus k1 minus k2 times q1 plus k2 divided by m times q2. Okay, do you see any q1 dot in this equation? Is there any q dot 1 in the first differential equation? Okay, so can I write plus 0 times q1 dot? Is that okay, mathematically speaking? Can I write plus 0 q2 dot? Is that okay? Can I write plus 0 times u? Is that okay too? Okay, so now we have everything that we need to have to go and complete the second row of matrix A and the second row of matrix B. So let's start with B because it has only one element. What should go as the third element of matrix B? Remember, I'm sorry, the second element. In the second row, we're telling this story, what Q1 double dot is. So what should be multiplied by U? 0, which comes right from here, the last element of the equation we found. Okay, so what is multiplied by the first element of X, which is Q1? It is minus minus K1 plus K2 in the numerator divided by M, and the negative applies to the whole fraction. And by the way, this is M1, so this is M1. This is M1. This is also M1, and this is also M1. Okay, so the next element in the second row, that element gets multiplied by what variable? By Q1 dot. What is that element? What is multiplied by Q1 dot? So the second element is 0. The third element gets multiplied by Q2. What is multiplied by Q2? What is multiplied by Q2? Absolutely. So K2 divided by M1. And what is multiplied by Q2 dot? Q2 dot? 0. So that's it. So we found the second row of matrix A as well as the second row of matrix B just by looking and rewriting at our differential equation. The last thing we need to do is to go back to the second differential equation and write and find Q2 double dot. So Q2 double dot is equal to 1 over M2. 1 over M2, and then we have to push everything to the other side. So we have 1 over M2, I'll make a bracket so I don't have to keep writing it. So what is multiplied by Q1 is K2, Q1. And what is multiplied by Q1 dot, guys, in the second equation? Q1 dot, what is the coefficient of Q1 dot? I'm talking about this second differential equation. In this second differential equation, what is multiplied by Q1 dot? There is no Q1 dot, so it's as if it's 0 multiplied by Q1 dot. So what is multiplied by Q2? So we found what is multiplied by Q2, and what is multiplied by Q2 dot is minus BQ2 dot, and what is multiplied by U is K3, and the whole thing is divided by M2. Questions? Is it clear what we are doing or why we are doing it? Okay, so let's go and populate the matrix. So what is multiplied by U, first of all? What should be the last element here? Just K3? If you K3 is divided by M2 in that bracket, so it's going to be K3 divided by M2. So K3 divided by M2 is the... So let's go back now to this portion. So the first question, what goes first is what is multiplied by Q1, which is what? What is multiplied by Q1? It is K2 divided by M2. So it's K2 divided by M2. Better. Okay, so what is multiplied by Q1 dot? 0. Q2, it is minus K2 plus K3 divided also by M2. So that's what is multiplied by Q2. And the last thing is what is multiplied by Q2 dot. So that is, what is it? It's minus B also divided by M2. We got it. So we have a 4 by 4 matrix for matrix A, and that is expected because the order of the system is 4. We have a 4 by 1 matrix for B. That is also expected because it's a fourth order system with one input. So 4 by 1. That's the reason. So what is left from our state space model? So we found A, we found B. The next matrix we need to find is, and that's the easier of all, because the only thing we need to decide is what is the output, and then immediately we'll have matrix C. So let's choose this. Let's say as choice number 1, we want our output to be, so choice number 1, we want the output to be Q1. The displacement of mass 1, that immediately tells you that, what is the matrix? Remember, X remains the same. X is still a column vector made of Q1, Q2, Q3, and Q4. So let me write X for this first one. So Q1 dot, Q2 dot, plus, of course, U, something multiplied by U. So this is, what is the dimension of X? This is 4 by 1. What is the dimension of Y? 1, what is it? Y is just a single number. So what is the dimension of a scalar? It's not a vector. So the dimension, this is a very good conversation. The dimension here is 1 by 1. That's the dimension. So it has 1 row, 1 column. Can you see that? Okay. So the dimension of Y is 1 by 1. The dimension of X is 4 by 1, 4 row, 1 column. So what should the dimension of C be? So that the result of multiplying C by a 4 by 1 is 1 by 1. It has to be 1 by 4. So it has to be a row vector. So now that we have settled that, tell me what are the components of this row vector. What goes first gets multiplied by Q1. So what should that number be? So this is 1. Then the next one gets multiplied by Q dot 1. What is that number? The next one gets multiplied by Q2. And the last one gets multiplied by Q dot 2. And they all get added together. So our matrix C for this choice of output is 1, 0, 0, 0. And obviously D is also 0. Because in the equation of Y equals Q1, there is no U. You can't see any U, so therefore matrix D is 0. So the second choice for output could be what? So let's say we want our output to be both of the positions, but not added to each other, because if we add the two positions, we can't distinguish how much each of the two masses move. So we want to keep them separate. So let's say we want our output to be Q1, Q2, both positions. That's our important. And I'm not going to write this out. I'm going to keep it as X. Okay, X is still 4 by 1. So what is the dimension of matrix C now? I'm going to ask the gentleman sitting on the second row on the right side of the class on the very far right. What is the dimension of C? Please think about it. I'll give you 30 seconds. Look at the analogy or the conversation we had for the first part. So what is the dimension of y? Let's think about that first. 2 by 2. The first number is number of rows, 2 by 1. So y in this case is 2 by 1. Okay? X is 4 by 1. So what should C be?
2 by 4.
And what is the reason for that?
Because you multiply them by each other.
So that the inner indices disappear and the outer two indices will tell us what the dimension. Yeah, very good. So this is going to be 2 by 4, which means it needs 2 rows and 4 columns. So tell me what the first row should be. The first row should give me Q1. So what should that first row be? That row is still multiplied by X. Anybody? Would you like to give it a try? So what do we want? We want that row to be multiplied by X, and what is produced is Q1. Haven't we already solved that problem in the first portion? So then the first row is simply 1, 0, 0, 0. Now, we want another row so that when it's multiplied by X, what comes out is Q2. So what should that be? What is that?
0, 0, 1, 0.
It is 0, 0, 1, 0. Can you explain how you found that answer?
I just looked at the original our state variable
Mm-hmm.
vector in the beginning.
Mm-hmm.
So
Which is Q1, Q1 dot, Q2, Q2 dot, and then what?
so just based off of that, the Q2's position in that is the third variable.
Mm-hmm.
0, 0, 1.
So the only thing that needs to remain on is the third one. Everything else needs to remain off, and off means 0. Make sense? Okay. Let's look at one more possibility. What if I told you I want them all? So I want y to include Q1, Q1 dot, Q2, and Q2 dot. All of them I care about. I want them all. I want to know exactly how this system behaves, both in displacement and velocity. So what is the dimension of y now? Do you want to give it a try? What is the dimension of y? How many rows, how many columns in y? 4 by 1. Because four rows, but 1 column. You don't see any other column. So this is 4 by 1. So 4 by 1. What is the dimension of my x? X is this. X is this vector. The dimension of x is 4 by 1 still. 4 rows, 1 column. So it's a column vector. So I want something that is, when it's multiplied by a 4 by 1, gives me 4 by 1. And what is the dimension of that thing? It has to be 4 by 4. So I'm going to write a 4 by 4 matrix. So 4 by 4. And x is 4 by 1. So you can see the two indices that are next to each other should match, and they would disappear. So what is left is what is on the outside. 4 and 1 remains for the product. So that's the rule. Okay, and there is no u in any of that, so this is going to be 0 times u. So tell me the rows of this matrix. Yes.
Just one in the diagonal and zeros everywhere else.
Are you telling me this is the identity matrix?
Yes.
Does that make sense mathematically? Because our y is exactly the same as x. So this is the identity matrix. It's like the number 1 in matrix language. So our y is exactly the same as x. So y is equal to x. So it is number 1, but number 1 of matrix language. So it's going to be 1, 1, 1, 1, and 0 elsewhere. So in other words, this is the identity matrix. So we looked at three possibilities, but there are a number of other possibilities. But you get the idea. No matter what possibility, the first portion of the state space model doesn't change. That's the most powerful feature of the state space model. That wasn't present in the transfer function. In your transfer function, when you wanted to find another output, you had to redo the whole transfer function. You couldn't keep portion and then keep. You couldn't, for example, keep the denominator and simply keep the numerator and change the numerator rather. But the benefit of the state space model is you capture the dynamic of system in one portion, and then no matter what output you want, you simply change only one matrix, which is in this case matrix C. And in rare cases, I said less than 1%, you may have to also change D. But that's the beauty and benefit of, or at least one of the beauty and benefits of the state space modeling. Okay, so we worked at this problem. Let's give you another problem to solve. This problem, you already have found A, B, C, and D of this system. Why don't you copy down A and B and C and D of this matrix, which is this system. This is a mass damper spring system with an applied force. We have already modeled this, both as differential equations, which later on we transfer to the state space model. Do you have the four matrices? A for this system was what? If I remember correctly, A was, please double check if you have your notes. My A was 0, 1, minus K over M minus B over M, 0, 1 over M for B. And if my output was the displacement, then my C matrix would be 1, 0, and D is 0. So I have the four matrices. And what should be clear, but this example should help you connect the dots even stronger. What should be clear is that all the models, all the three models of this system are equivalent to each other. Why? All three models, differential equation, transfer function, state space, they're equivalent to each other. You can start from one and get to the other one. Why they are equivalent to each other? Because the root of all three is the same. You start from Newton's second law, you get to differential equation. From differential equation, you go to Laplace domain, you get to the transfer function. From the differential equation, you rewrite the equations in the form of matrix, you get to your state space model. So they're essentially carrying the same information. So what this is tries to give is by applying this equation at the top. By the way, we already know the transfer function for this system, don't we? We have already found the transfer function. The transfer function between force and displacement is what? Can someone look it up? If I remember it correctly, G of S, which was X of S over F of S, displacement over force was what? Was it 1 over ms squared plus bs plus k? Is that what we found, or something else was in the numerator? That's what I'm not sure. Was it 1 over ms squared plus bs plus k? Okay, so we do have the state space model. We do have the transfer function. What I want you to see is you can start from the state space model and arrive at the transfer function. Imagine this again. The root of all three models is the differential equation. So to get to the state space model, we started from the differential equation. To get to the transfer function, we started from the differential equation. I want to show you now you can go between the last two and arrive at the same answer. So you can start from the state space model and get to transfer function. And that's the purpose of that formula at the top. It tells you the transfer function is matrix C, which is part of the state space model, times S times I, which is identity matrix, and S is the Laplace variable, minus A, which is part of the state space model, inverse of that matrix, multiplied by B, which is part of the state space model, plus D. Go ahead and apply this, please. Go ahead and apply this formula, knowing what A, B, C, and D are. Apply this formula and see if you can get to this transfer function. Sorry about that. So we have the four matrices and we have the formula. We want to apply the formula to see if we can get to the transfer function, which we know the answer, so we are just verifying that. Okay, so the formula, the first part of it calls for CS was it CS? No, SI rather. So it calls for SI minus A inverse. So before finding inverse, let's find SI minus A. Now SI means this. The identity matrix in this dimension, which is 2 by 2, everything has to be the same dimension. What is SI? SI is going to be, whereas A will turn to S. So let me write one more step. So it's S times the identity matrix, which is 1, 0, 0, 1, minus A, which is 0, 1, minus K over M, minus B over M. That is SI minus A. Now, the resulting matrix would be, now SI becomes S0, 0, S. So whereas 1 will turn into S, whereas 0 remains 0. Now, we need to take S and subtract from it what? What element gets subtracted from this first element? The same counterpart on the second matrix. So the result would be S minus, and S minus what?
0.
So let me rewrite. So this becomes S 0, 0, S minus 0, 1 minus K over M minus B over M. So the result becomes S minus 0, which is S, 0 minus 1, which is minus 1, 0 minus K over M, which is K over M, S minus B over M, which would be S plus B over M. Did you see that? Tell me if something doesn't make sense, or did we make any sign mistakes or multiplication mistakes? Just verify. I'll give you a few seconds to go over it. Yes, sir.
Did we ever multiply C with A?
As part of the formula?
Oh, never mind.
So the first part was to find SI minus A first. So we are going from inside out. The next step is to find inverse of this matrix. So we found SI minus A. Let's go ahead and find the inverse. So SI minus A inverse. We said what we will we do when we have a 2 by 2 matrix? We switch the diagonal elements and we change sign of the off diagonal elements and divided by the determinant. So it's going to be another 2 by 2 matrix. S plus B over M comes here. This becomes 1. This becomes minus K over M. And this becomes S divided by, now what is the determinant of this matrix? Determinant of Si minus A, that is. So how do we find determinant of a 2 by 2 matrix? We multiply the diagonal elements. If you multiply that, you get S squared plus B over M S minus the result of multiplication of the off diagonal elements. So what would that be? Minus what? It would be positive K over. So that's the determinant. What is the next step? According to the formula, I need to take this and pre-multiply it by C. What is my C? C is 1, 0. So 1, 0 is of what dimension? C is of what dimension? What is the dimension of C? It's how many rows? 1 row, how many columns? So it's 1 by 2 multiplied by a 2 by 2. So the result is what? What dimension? 1 by 2 multiplied by 2 by 2. The result of the dimension of the result is? So let's rewrite it. So we are multiplying a matrix C, but by Si minus A inverse. C is 1 by 2. This is 2 by 2. So the result would be of what dimension? We said the inner two matrices, the inner two indices will disappear. The result will come from the outer two indices. So what is the result? The dimension of the result? From here, we have 1. From here, we have the outer, which is 2. So the result would be 1 by 2. Can you now see that? So if you multiply, pre-multiply Si minus A inverse, which we already found, by C, the result would be 1 by 2. Clear? Yes? Okay. Okay, so let's, yes, sir.
So like earlier you got a 4 by 4 by multiplying 1 by 4 by 1 by 4.
Let's go to that slide.
Technically would have been a 1 by 4.
Which one is that?
4 by 1.
So is it on this? Let me resize. This one? Okay. So this is 4 by 1. This is 4 by 4 multiplied by 4 by 1. So the inner two indices of 4 and 4 will disappear. So the result is 4 by 1. Did we miss something?
No, I get it now.
Okay. Any other questions? I'm very glad we're having the conversation. So I really need your feedback. Okay? So tell me if something doesn't make sense. And if something does make sense, maybe nod or say something. Or we're not trying to replicate the British Parliament here, but something in between would be helpful. So if I know that you know, it is helpful. Or if you don't know, please stop me at any time. That's what we are trying to achieve. Okay, so the result we know is going to be 1 by 2. So 1 row, 2 columns. 1 row, 2 columns. So let's go ahead and do the multiplication. So 1 row, 2 columns. So this is C, 1 by 0. And this is Si minus A. I have it there. So let's go ahead and carry out the multiplication. So C times Si minus A inverse is going to be equal to, I'm not going to copy C because C is right here. So 1, 0, this row gets first of all multiplied by the first column of this. So 1 gets multiplied by what of the two elements of the first column? 1 gets multiplied by s plus b over m, and 0 gets multiplied by minus k over m. So minus k over m will not survive. What will survive is s plus b over m. Now, again, c, the same row will be multiplied by the second column, which means 1 gets multiplied by 1 and 0 gets multiplied by s. Can you see that? And what is left is 1. So this is a 1 by 2 matrix, and we shouldn't forget the determinant. So this carries over. So far we have completed a couple of steps. So C times Si minus A inverse is found. We pre-multiplied by C. We know the result. Then we need to go up and see what is left. What is left? B. Okay. So we need to now post-multiply it. I keep repeating pre and post because in matrix multiplication, guys, the order does matter. So you can't simply switch C and B in places because in this case you can't even carry out the multiplication. The dimensions should match before you can do the multiplications. So we're going to post multiply the whole thing by B. Okay, so we know the result, and B is right there. B is a column matrix. I'm sorry, a column vector rather. It just has one column. And how do you multiply C times Si minus A inverse, which is, what is the dimension of C Si minus A inverse? It is 1 by 2, and we are multiplying that by 2 by 1. So what is the resulting dimension? So let me rewrite what I said. This entire thing is of dimension 1 row, 2 columns. Can you see that? It's right here. It has 1 row, 2 columns. Can everybody see that? Okay. Now what is the dimension of B? If you look up here, B is what? It's 2 rows, 1 column. So you're multiplying this by 2 by 1. So what is the resulting dimension? It is a number. It's no longer a matrix. So what you will do in that multiplication is you get this row of s plus b over m and 1, and multiply it by this column. So the s term gets multiplied by 0, and the 1 term gets multiplied by 1 over m. So what survives is simply 1 over m. So it's 1 over m. That's the result of multiplying the two matrices. Of course, we can't forget the determinant. So s squared plus b over m s plus k over m. And of course, d is 0, so we don't have to add anything to it. According to the formula, there's a plus d, but d is 0, so we're there. So if you simplify that, which means multiply both the numerator and the denominator by m, you get 1 over s squared plus b times s plus k, and there's an m here. Did you see what we did? We applied the formula. We started from the state space model and we arrived at the transfer function. So that should emphasize, that's the whole point of this exercise, to re-emphasize that all of these models are equivalent to each other. They're not different. So you can start from 1 and get to any other 2. Any questions before we switch gears a little bit here? Okay, so the next subject is the whole concept of electromechanical systems. So far, we have kept everything nice and separate in the sense that when we were talking about mechanical systems, we didn't bring any fluid flow into it or any heat transfer into it. Or when we talked about an electric circuit, we kept the mechanical system out. We didn't bring any mechanical systems in. But the reality is, we never have a system that has only one physics. Always these are mixed in any practical applications. And one of the domains, or the two domains that we will bring together as our initial attempt of multi-physics modeling, is electrical and mechanical systems together. And if you look anywhere, as close as to your cell phone, you can see that the electrical system comes and it gets combined with mechanical systems. What would be an example in your cell phone that you have an electromechanical system? So you have motion. When we say mechanical, it means motion. We have motion and we have electricity. Of course, we're not talking about motion of your fingers scrolling up and down. We're talking about something inside the cell. Anything? Yes?
I don't know about a cell phone, but if you had like not a solid state hard drive, which is a regular hard drive, you have like the spinning
Yes.
disk.
Yeah. So you have a motor there. And in all your cell phones, you have a motor. At least it used to be like that. The way you create vibration in a cell phone is you have a motor that has a mass that intentionally is off balance. It's like your tire, you try to balance it, but there you intentionally cut that mass into half. So it's a half cylinder. It's a half cylinder attached to a shaft of a motor. And as the motor spins, it creates that something that you want to avoid in your car, but just creates vibration. So that's how vibrators in cell phones work. So we have the point is we have a lot of electromechanical systems. Now, remember back to basics. We said every time we have a system, we go back to their physics and see what law applies. So we write that law and try to turn that law into a math equation. That's how we worked so far. This is no exception. Whenever we have electricity and mechanics or motion combined, we have to look at the basic laws. And there are two basic laws. The first law is law of motors, which is you can guess by the name, it is the basic idea of how motors work, or at least DC motors work. It essentially says it's a simplification of a more complex or general rule. But if you assume that you have a conductor, like a wire, that carries a current, imagine that. So you have a wire that carries current, and this happened to be in a magnetic field that is perpendicular to the current. Imagine that. So you have a wire carrying a current I in a magnetic field with the strength of B, capital B, and the length of that wire is lowercase l. So we have three variables: current I, the length of the conductor, and the strength of the magnetic field. The law of motor says if you have this scenario, if you have a wire of length A carrying current I in a magnetic field that is perpendicular to the direction of the current, this interaction will create a force F that is equal to B times L times I, and not only that, the direction would be perpendicular to both direction of I and direction of B, following the right-hand rule. So if your thumb is aligned with your magnetic field, for example, and the second finger is aligned with the current, the middle finger would tell you the direction of the force. Can you see that? So current, magnetic field will create a force. So that's the law of motors. So whenever you have a conductor in a magnetic field carrying a current, the result would be creation of force. And that is the basic idea of DC motors. That's the basic idea of DC motors. You intentionally create magnetic field. You pass electricity through a wire winding, and that the result is rotation, and we'll get to that. So that's law number one. Any questions on this law? This is law of motors. Okay, so the second law is law of generators. Similarly, but this time we intentionally move our conductor within a magnetic field. So the law says if you have a conductor again of length L, moving perpendicular to a magnetic field B, so the motion this time is perpendicular to the direction of the magnetic field, you will create a voltage. You will create a potential, electricity potential, that is equal to B times L times V, which is the velocity of travel. Please don't mix up V and E. E is the voltage, V is velocity. So if the direction of velocity, again, is with your thumb, and the direction of magnetic field with the second finger, the direction of applied voltage is defined by the third finger. Again, the right hand rule applies. So two laws. You're ready to apply them? I can tell you're ready to apply them. So we are going to apply them here in this motor. So a motor basically is a collection of conductors in a magnetic field. It's a collection of conductors in a magnetic field, and our intention is to create motion. We want to create a rotation at the shaft of this system. So our goal here would be to come up with a model for this system. We want to come up with the model of how this system works. Now you can appreciate that there is the electric side. We have a circuit. We have a source of voltage. The wire winding has a resistance. It also has an inductance. Whenever you create a coil of wire, you create an inductance. So we are going to write an equation for the electric part. We are going to write an equation for the mechanical part, because whenever you have a motor, it's going to move something. There is a load, a mechanical inertia element attached to it. So we are going to include that. We are going to include friction in that. So we are going to write Newton's second law in rotational form. We are going to write Kirchhoff's law for the electric side, but we are also going to take advantage of law of motors to find out how much torque basically is created in the motor. Clear? Now imagine this. I told you if you have a conductor in a magnetic field and you pass current through it, what will happen? Let me ask my question one more time. In the motor, what we have is a conductor in a magnetic field and we pass current through it. What will happen? What will be generated as a result? A force. If you apply a current in a magnetic field, is force. If you move your conductor in a magnetic field, you create voltage. That's the generation. Okay, so there would be a force. There would be a force, which means what? Which means now this conductor will start moving. Would it start moving in a magnetic field? Now we have a conductor that is moving in a magnetic field. What would be the result? The law of generators. You will generate voltage in that conductor. Let me review what I said. You have a conductor, you pass current through it, and it starts moving. There would be a force, and that force, by the design of this motor, will cause this rotor, which carries the conductors, to start rotating. Now, as soon as you have a conductor that moves in a magnetic field, according to the second law of generators, you start generating voltage in that conductor. And unfortunately, this is not a perpetual motion machine. So that voltage is actually opposing the voltage that you apply to get the whole thing to move. So the point is, whenever you have a wire winding that rotates in a magnetic field because you have applied a voltage, there would be a secondary voltage generated that is unwanted. It's like friction, but it's in an electrical type friction. So you create an opposing force, which is an opposing voltage in this case. So we are going to take that also into account. This is in the language of modeling called, or this type of system is called back EMF, or back electromotive force. So it's like a friction. So we will take that into account. So in a way, we are laying the groundwork. We are saying what should be included in the model, and then next we'll go and include it. So what should be included so far? It should be the electric circuit, obviously. We have to have the circuit. We should have should have the mechanical side, but we also should have the side that connects the mechanical side and electrical side. And there are two things that connect them. One is law of motors, which tells you there is a torque will be created as the result of existence of magnetic field and voltage. And the second one is the law of generators that will tell you you will create an unwanted voltage that would oppose the main voltage in the circuit. Clear? Okay, let's go ahead and look at the equations. So let's focus first on the electric side. In the electric side, if you law Kirchhoff's law, you have the source of voltage, V, which will create a current here. And that current is what we show as I in the middle with this curly arrow. So that's the current. And we have to add all the voltage drops to create the equation. So this is the Kirchhoff equation. So you recognize L di over dt, that's the result of the inductance. You recognize R times I, that's the voltage drop across what element? R times I? The resistor. What is capital V? Capital V is the applied voltage. Now there is an element that is not as familiar, and that is K times theta dot. Now let me talk about theta for a second. Theta is angular position or angular rotation of the shaft of the motor. So the shaft of motor, how much it rotates, is captured with angle theta. Okay? Now think of law of motors for a second. Let's think of law of generators actually for a second. Law of generators tells you the amount of E voltage that you create is equal to the strength of magnetic field B, the length of the conductor L, and velocity of travel of the conductor. Velocity of travel of the conductor. Now, when you look at a coil of a motor, if I want to draw one, so on the cross section you see a circle rather, but the conductors are lined like that. Can you see that? So there is this radius, so this is the radius, and the rotation is captured with angle theta and velocity of theta dot. And the whole thing is in a magnetic field. So the whole thing is within a magnetic field. Let's say these are the north and south of magnet to represent that magnetic field. So the whole thing happens in this B magnetic field. Okay? So each of these wires are moving at a velocity. What is that velocity? Now, what law of generators is looking for is that velocity. So let me move this. So we need the velocity. So if you have a cylinder at a radius r and it's moving at angular velocity of theta dot, what is the linear velocity of the points that are on the perimeter? Aren't they r theta dot? It is r theta dot. So this is going to be B, strength of magnetic field, L, length of the conductor, times r times theta dot. And this is E, generated voltage, as the result of law of generators. Now, B, magnetic field, is constant, isn't it? The magnetic field, we try to keep it constant. Length of the conductor doesn't change. It's the same coil that keeps rotating and rotating. The radius of the coil is not also changing with time. So that's why you can call the entire BLR variable K. So it's K theta dot, how much voltage is generated as the result of revolving this coil in the magnetic field. This is again called back EMF, the voltage that is generated that you don't want it to be generated. So that's why when you come to this equation, that voltage is opposing the actual voltage that derives the circuit. So this is minus k theta dot. So this is E, back EMF. That should now make the Kirchhoff equation a little bit more clear. What the four elements in the electric side is. So let's review. This is Li dot is voltage drop of the inductor. Ri is voltage drop of the resistor. V is the actual voltage driving the circuit. And minus k theta dot is the voltage generated as the result of motion of the conductor in the magnetic field. So it's like a generator, generating voltage in the unwanted direction. Clear so far? Now, just look at that equation. Isn't that an equation for an electric circuit? That's an equation for an electric circuit. But what is different about it? What is different about it is it also, like any other electric circuit, it has voltage and current. But do you see something extra in it that is unusual for an electric circuit? What I'm referring to is theta dot. What is theta dot? Is it a current? Is it a voltage? No, it's a variable that captures mechanical rotation. And that's the nature of systems that have multi-physics in them. So in their equations, you have variables from both domains. So in that equation, you see current and you see voltage, but you also see angular velocity. Clear? Okay, so let's now move to our Newton's second law. What we have here, what says J and B theta dot and theta and T, this is basically the free body diagram. The free body diagram. So that shows the initial element that is attached to the shaft of the motor. It's shown as a disc, but it doesn't have to be a disc. Anything that rotates, even the winding assembly itself has some inertia. So it's everything that has inertia and moves with the motor. Okay, so according to Newton's second law, J theta double dot, so J theta double dot is equal to sum of all the moments or torques applied to this system. Now, what are the externally applied moments? One is T, which comes from the interaction of the coil and the magnetic field and the fact that a current passes through it. That comes from law of motors. The other one is friction. Whatever slows this down, and we use a viscous friction, so it's B theta dot. So it's proportional to how fast it moves. So if you look at law of motors, according to law of motors, actually law of motors basically says F, force generated, is equal to B, strength of magnetic field, times L, times strength of current passing through the conductor, through the wire. Now, in the case of a coil that is winding around the cylinder, like what we have in a DC motor, we are not looking for the linear force. We are rather looking for the torque or moment. And we know that moment is R, the distance, to the center times F. So if you want to get to the torque, what you would do is you multiply R by F, and we'll call it the torque applied through the law of motors, and this is going to be R, B, L times I. R, B, L times I. Haven't you seen R times L times B elsewhere on this slide? Look at the very top. What did we call R times L times B? We called it K. So the torque applied to the rotor is K times current. Can you see that? So this is K times the current. And that's exactly what you see here. This is Newton's second law. Basically says there are two externally applied torques. One of them is K times I with a negative sign. Let me include the negative sign. So it is equal to minus K times I. And the other one is friction, also with a negative sign. So minus B theta dot. If you bring B theta dot to the other side, I apologize, Ki is positive, is deriving the circuit. I made a mistake. So this should be positive. So, and you can see the direction. This is the deriving, this is opposing. So that's why their signs are different. So you have plus Ki, which is the torque that derives the whole thing, minus B theta dot, which is what slows down. If you take B theta dot to the other side, you get to this equation. Is there anything that we haven't included in the behavior of the motor? So far, we have two equations. One is the equation of the electric side, or at least driven by the electric side. The other one is mechanical side. But look at the equation, the Newton's second law of mechanical side that we got. What is unusual in that equation? What is there that typically doesn't belong to a Newton's second law? You have your J theta double dot, that's a typical part of a Newton's second law. You have your B theta dot, that's typical, that's the effect of friction or damping. But what is atypical is having a current in Newton's second law. And that's because this is an electromechanical system, we have current in this. Okay, so what is the order of this system? Why do you call it a second order? Which equation do you look at and call it a second order system? So you have theta double dot, and that captures the mechanical part of it. But is an electric part also part of the same system, which is captured by the second equation? So this is the very first system that is, we have investigated, and it's a third order system. So it has three state variables. Okay, so it's your challenge now to write the state space model for this system. So it has, we know it's a third order system, which means it has three state variables. So let me rewrite the two differential equations here. So the first one was J theta double dot plus B theta dot equals K times I. And the second equation was what? It was L di over dt plus Ri plus K theta dot was equal to V. So there are two differential equations involved. Should we do state space first and then transfer function, or go the other way around? We can do anything you want. But before doing anything, we need to define what the input of the system is. What is the input? We need to decide about the output of the system. And also we need to decide about the state vector. So input. It makes sense for the input to be the voltage applied, V. Output. What is the whole purpose of a motor? To do what? To generate power, but in the language of what we have here is we can say to generate the rotational displacement. You need to create some rotation. Of course, you have to overcome the inertia to create that rotation. Or you can say, no, the purpose of my motor is to give me a certain RPM. So based on what you want, what is the purpose of this model, your output would be either theta or theta dot, or you can say, no, I really also need to monitor the current in the circuit. That's it's going to tell me how efficient my motor is. Then the current could also be that. So for now, let's keep it open. Keep our options open for now. But let's talk about state variables. What are the state variables? From the first differential equation, what are the state variables?
Theta dot.
Absolutely. Theta and theta dot are the two state variables from the first. How about from the second? Can't have a steady.
I.
That's a very important point. I got that answer that from the second differential equation, I get two more state variables, and they're I and I dot. Let me remind you of one fact, that number of state variables are equal to order of the differential equation. So the first differential equation gave us two state variables because it's a second order differential equation. The second one is what order differential equation? What is the highest time derivative? It's 1. So therefore, it can only give one state variable. And what is that state variable? What variable is being time differentiated? Current. So current I is the third state variable, and that further emphasizes the fact that we are dealing with an electromechanical system. Look at the state variables. Two of them are mechanical, one of them is electrical. So they're all combined into one state vector, which is a column vector. The little t says it's a column vector. Okay, should we do it? Should we write the model? So let's go. The first step is to find x dot. This is going to be a 3 by 3 matrix times x plus a 3 by 1 times u. So the first member of x dot is theta dot, and that's equal to the second member of x, which tells me row 1 of this has to be 0, 1, 0, and a 0 here for input. That's very similar to what we did for mass spring damper system. The second member of x dot is theta double dot. And theta double dot, according to the first differential equation, is a function of theta dot and I. Can you see that? That theta double dot is a function of I and theta dot. So there is no theta in theta double dot. So that tells me the first element is 0. What is multiplied by theta dot is minus b over j. What is multiplied by I is plus k divided by j. And again, there is no voltage in that equation, so it's 0. So what did we do? We rewrote this first differential equation to get theta dot in terms of theta dot and I. There is no theta, so the first element is 0. There is minus b times theta dot. That's why second element is minus b over j. And k over j times I, so that's k over j is the last element of the second row. Now let's go to the last row. What does the last row show? It basically shows how I changes with time. So what is I dot in terms of these three state variables? Now, is I dot function of theta? Do you see any theta in the second differential equation? In the second differential equation, do you see theta? You don't see theta, so this is 0. Do you see theta dot? Yes, you do, with a negative sign. So you see minus k divided by L. Do you see I? Of course, you see R divided by L, also with a negative sign. Do you see the input V? Of course, you see it with a positive sign, divided by L. So 1 over L. So we have matrix A, matrix B. Any questions?
How'd you get the 1 over
So if you rewrite this equation to single I dot out, you have to divide everything by L. And that's what the third element of X dot is. The third element of X is I, so the third element of X dot is I dot, di over dt. So we are trying to find di over dt from the second differential equation. Okay, so the second part of the state space model is the output portion. So what is Y? And depending on what Y is, your matrix C would be determined. So if Y is theta, the position, your C matrix would be 1, 0, 0. If your output is, for example, the position and velocity both, you have 1, 0, 0, 0, 1, 0 times x, and plus 0 times u. This gives you both position and velocity. If you want all of them, then y becomes the identity matrix times x plus 0u. So there are multiple possibilities with the output depending on the purpose of the model, and each of those possibilities will give you a different C matrix. Nothing else will change. A and B and D are going to remain the same, but the C matrix could change to reflect the choice of output. And if you hadn't seen the differential equation, and the first thing that was given to you was this state space model, could you tell that this is a third order system simply by looking at the state space model? You could. How? Where would you look to tell that this is a third order system? The dimension of matrix A is the telling sign. So matrix A is 3 by 3. That tells you this is a third order system. Okay? So your next question is to find now. So we started from differential equation. We got the state space model. The last type of model we can do is a transfer function. So I'll let you do this. So find a transfer function, g of s, between output theta of s and input v of s. So I'll give you a minute to find this. So how do you solve that problem? How do you find the transfer function model? What are the basic steps? To Laplace transform both of these differential equations, and the benefit of doing that is as soon as you go through the Laplace domain, you no longer have to deal with differential equations. So you can apply algebra and manipulate your equation. So let's do that. Remember always, please, that all initial conditions are assumed to be equal to 0. So what are assumed to be equal to 0? We are assuming theta at time 0 is 0, theta dot at time 0 is 0, and the current at time 0 is 0. So we are making that assumption in order to have a simplified version of the Laplace transform. So if you transform this to a Laplace domain, what will you get? The first equation. I'm waiting for you guys. So j is constant, so it becomes js squared. What do you get from the second one? You get b times s, and the whole thing will be multiplied by what of s? Theta of s. And on the other side, you have k times I of s. There is no differentiation involved on the other side. So that's the first differential equation. The second one, the same way, you have L times S plus R. This is multiplied by I of S plus Ks theta of S is equal to V of S. So from the very first equation, you can get a transfer function between I and theta. Look at the first equation. From that, you can get a transfer function very easily between I and theta. The relationship between current and displacement is very clear from that equation. From the second, you have relationship between three variables. You have I, you have theta, and you have V. So if you want to get rid of I, because your interest is in relationship between V and theta, you need to take advantage of the first equation and substitute for I in the second equation. So let me write what I said. So from the first equation, you get I of s as j s squared plus bs over k times theta of s. Do you agree that this is I of s? Yes? So then what I will do, I'll rewrite the second equation, but instead of writing I of s, I'll substitute for I of s based on what I found from the first equation. So what will I do? I'll write ls plus r, but I will not write I of s. I'll write js squared plus bs over k times theta of s. Plus, then I'll continue with the second equation, plus ks theta of s, and that is equal to v of s. Now we're ready to form our transfer function, because we now have only two variables. We have theta of s, which is the output, and we have v of s, which is the input, so we can create the ratio. Now, I have to do some algebra, so we need to make k the common denominator, for example. If we make k common denominator, this becomes k squared times s. So what we will have is, so 1 over k multiplied by, I can multiply this through, so it would be L J S cubed plus L B S squared plus R J S squared plus R B S plus K squared S. All of this is multiplied by theta of S, and that is equal to V of S. So if you're looking for a transfer function between theta as output and V as input of a big ratio where K is the numerator and the denominator is L J S cubed plus LB plus RJ times S squared plus RBS plus, let me rewrite this, plus RB plus K squared multiplied by S. Okay, so what is the order of the system? Third order. So you can see that also from the transfer function. Please check the math. If I missed anything, let me know. Yes.
If you were, so you multiply by K to get that K squared S
Mm-hmm.
in the second line from the bottom.
Mm-hmm.
If you were to do that, wouldn't that 1 over K go away?
If we multiply by K, so what we did is look at this equation, the third from the bottom.
Yeah.
So I made K the common denominator between everything.
Mm-hmm.
So K stays here, but this has to become K squared. So my point is, if you want to have a denominator of K here, this has to become K squared. So currently K is only denominator of the first ratio, and then not the denominator of the second. If I want to add these together, they need to have the common denominator.
Gotcha.
Okay. Now, here's a challenge question. I'll leave you with this challenge question. The challenge question is, if you, let me write it on a slide so you have it when you look back so you know what the challenging question is. If you want a transfer function between voltage and angular velocity, you want a transfer function between voltage and angular velocity, what that transfer function will be. That's my challenge question, and I'll leave you with that. So